All right, so in the last video, we did this factoring, and we discovered that there are these two complex zeros, 1 plus 2i and 1 minus 2i. We got those from the quadratic formula here. These are called conjugates. The 1 plus 2i and the 1 minus 2i. They're called conjugates. Conjugates, you may have encountered the idea of a conjugate before when doing something called rationalizing a denominator of a fraction. Whenever you have like a plus b and a minus b or something like that, where you multiply them together and you get that difference of squares, those are called conjugates. So there's two kind of situations in which we talk about conjugates. One is with irrational numbers, where you have the sum of a rational number and the square root, or like an integer and the square root of an integer, which is not a perfect square. That produces an irrational number, and these would be called irrational conjugates. And the other situation is with complex numbers, where you have real numbers a and b is multiplied by I. So you have the real part and the imaginary part. And then whether you have a plus bi or a minus bi, those two together, those are called complex conjugates. So there's this theorem that deals with polynomial zeros and conjugates. And it turns out it is no coincidence that in this example we ended up with two conjugate zeros. And the reason is because the coefficients of this original polynomial we started with, these were all real numbers. Because the theorem says this: if a polynomial f of x has rational coefficients, so that would be like fractions, integers, that kind of thing. Not irrational numbers, okay, but rational numbers as coefficients. Then any irrational zeros that it has have to come in conjugate pairs of this form. And likewise, if a polynomial f of x has real coefficients, okay, which would include rational numbers, but also irrationals and that sort of thing, then any complex, specifically imaginary, like complex imaginary non-real zeros have to also come in conjugate pairs of this form, a plus bi and a minus bi. Now, I like to refer to this theorem as the buddy theorem, because I have an analogy for this. So it goes like this: if you are a number and you are invited to a party, and all the other people going to this party are rational numbers, but you're an irrational number, then since it's a party for rational numbers, but someone invited you anyway, you're maybe feeling a little awkward, and you're like, maybe I don't really fit in at this party. So you want to go, and you can't change yourself. You know, you are who you are. You are an irrational number, okay? You're not going to change yourself, but you might feel a little more comfortable at that party if you bring your buddy along with you. So your irrational self and your other irrational buddy, you go together, and you feel comfortable if you are together. And similarly, if it's a party for real numbers and you're a complex number, you want to go to that party with your buddy. So that's how I like to think about this. So that's kind of a nice way to remember that these things always have to come in pairs with one another. So let's look at an example. Okay. And this is a bit of a contrived example, but the whole point of the example is just for you to like wrap your head around how this theorem works. Okay. So it goes like this. Let's say that you have a polynomial f of x, and its coefficients are integers. Okay, all of the examples that we've done have integer coefficients. And to be honest, the study of polynomials largely revolves around integer coefficients. Not exclusively, of course, especially when you get to like applications with modeling and stuff, you might use like whatever kind of coefficients you want, but usually you are at least dealing with rational coefficients, and those can be sort of like simplified into integer coefficients just by like clearing denominators. So let's focus on that. You have a polynomial with integer coefficients, and it has some roots. Let's say you know it has roots 2, square root of 3, and 1 plus 2i. we're going to find the simplest such function, f of x. The simplest function f of x could possibly be. So, since we know that these three numbers are zeros, and since we know that the coefficients are integers, both versions of the conjugate pairs theorem here have to apply, okay? Because integers count as both rational and real numbers. So 2 is fine. 2 is fine going to this party by themselves, because 2 is an integer, and in particular a rational and a real number, so they're totally comfortable going to the party alone. Square root of 3, though, is irrational, right? So the square root of 3 being irrational is only going to go to this party with their buddy, the negative square root of 3. So I'm going to make a list of other zeros that are required in order for this to work. We're going to have negative square root of 3, because if you have like 0 plus the square root of 3, you're going to have 0 minus the square root of 3. So when you have just a square root number, like, you have to have the opposite of that as well. These are the conjugates of one another. And then, of course, 1 plus 2i is a complex number. So it's got to go to the party with its buddy, and its buddy is 1 minus 2i. So we don't just have 3 zeros. We actually have 1, 2, 3, 4, 5 zeros. So this function we're working with here is going to have to be, its degree is going to be at least 5. And I can write it out in factored form. And it's going to look like this. So each of these zeros is going to correspond to exactly one factor. The first factor, I'll do x minus 2. And then we'll go ahead and do the factors for the irrational numbers, x minus the square root of 3. And then x minus the negative square root of 3, which becomes x plus the square root of 3. And then we'll do it for the complex numbers, x minus, and I like to put complex numbers if they have two terms, I like to put them in parentheses. So x minus 1 plus 2i in parentheses. And then we're going to have for the other complex conjugate, x minus 1 minus 2i in parentheses. So each of these zeros corresponds to one of these factors. And technically, we have found the simplest, this here is the simplest polynomial function that satisfies these requirements. But this might not feel like a very satisfying conclusion because this doesn't look much like a polynomial. It is, right? It is. It's just in factored form, right? So what we can do, we spent all this time learning about how to factor polynomials so that we can solve equations. But if you start with a factored format, you can convert it back to your like a full sort of simplest, what it's called, standard format, I guess. You can convert it back by basically expanding everything, foiling everything out. And the strategic way to do that is to take pairs of factors 2 at a time that correspond to conjugates. So let's see what happens if we multiply out x minus root 3 times x plus root 3. We get x times x, x squared. Then we get x times positive root 3, so plus root 3 times x. And then negative root 3 times x. And we get negative root 3 times positive root 3. Negative times positive is negative, and the square root of 3 times itself is going to be 3. So in that situation, the plus root 3x and the minus root 3x are just going to cancel out. Now we still have this x minus 2 over here. Now let's do this one. Now this one's a little harder. We're going to have x times x is x squared. Then we'll have x times the negative 1 minus 2i. And so that's going to be negative 1 minus 2i times x. I'll distribute that in a minute. Then we're going to have the next term, so negative 1 plus 2i times x, so minus 1 plus 2i times x. And finally we have 1, or negative times negative is positive, 1 plus 2i times 1 minus 2i. So let's multiply that out. We're going to have 1 times 1, and then 1 times negative 2i, and then positive 2i times 1, and then positive 2i times negative 2i is going to be negative 4i squared. I almost ran out of space there. We have a plus 2i and a minus 2i that are going to cancel out. So let's get back to that. We're going to have x squared. I'm going to distribute this x multiplication and this x multiplication. we're going to have minus x plus 2ix, and then we're going to have another minus x and a minus 2ix. And then here we're going to have plus 1 and then minus 4i squared here, since I squared equals -1. The negative 4 is times -1, which actually gives us plus 4. So that's that whole thing. So in here, some stuff is going to cancel out. We have plus 2ix and minus 2ix. That's gone. The minus x and the minus x, instead of canceling, are going to combine. So we'll have x squared minus 2x. And then the plus 1 and the plus 4 will combine like that. All right, so over here, x squared minus 3. And then over here, x minus 2. And here's what I have so far. Okay, this is a wacky thing. So now I can start, now that I've basically completed, I've completed doing all of the conjugate pair expanding. And so this, by the way, this point in the process right here, this shows you why we need the conjugates. And the reason is because having the conjugate pairs causes all of the irrational parts to cancel out right here. Like all the irrational bits cancel out, and now we only have integers as coefficients. And then over here in the complex version, all of the complex numbers canceled out, right? The plus 2i, the minus 2i, all that stuff all canceled. And again, we just have real number integer coefficients when we're done. So that shows you why you really need those pairs to come together. It's because in expanding them, that's what allows all the bits that aren't integers to cancel out, leaving you with only integer coefficients. Now I'll stop here, but you can keep going, and you can continue with the foiling and the multiplying out and all that jazz, and get down to a nice simplified format. And you can check that if you want. But that's it. That's pretty much it. Okay, that is our exploration of polynomials and factoring polynomials. That's how you solve polynomial equations. The strategies we've learned in this chapter 5 don't cover all possible polynomials, but they give you a lot more power than you had before to solve equations. So that's it.